Good morning, good afternoon, and good evening, everyone. Thanks so much for joining us today. This is our first webinar of 2021, and we're focusing on machine modeling with the RTDS Simulator. I'm Katie Sidwell from RTDS Technologies, and I'm here, by which I mean not physically, but in spirit, here with my colleague, machine specialist, Dr. Ali Dekordi. Today's webinar will follow a similar format to our in-house applications webinars from last year. So I'll begin by providing a brief introduction to the company and to the RTDS simulator, including some machine modeling applications at a high level, and then I'll turn it over to Ali, and he will present in more detail on our various machine models, and then he'll go into a 25-minute demonstration in the RSCAD software showing the transient simulation of a generator as well as its protection and control. We don't actually have any hardware in the loop today in the demonstration. It's all software, but we'll talk a little bit more about considerations for interfacing physical equipment, such as a generator protection relay or various control devices. After the demo, we should have quite a bit of time for Q&A, and I highly recommend you take advantage of Ali's expertise here, and we can dig into the machine modeling theory and capabilities a little bit more. I also wanted to mention at this point that we're hoping to do some more machine modeling webinars later this year, perhaps focusing more on polyphase machines for renewable applications and electric ships as well. So I hope you're interested in this type of webinar, which is a little more focused on modeling aspects and simulated protection and control rather than interfacing physical equipment. You can let us know your thoughts on that in a poll question at the end of the webinar. Speaking of which, a few housekeeping notes. Please feel free to submit your questions throughout the webinar. You don't need to wait until the end. You can submit them via the Q&A panel. If you submit via the chat, we might not see your question, so please do use the Q&A widget for that. If you want to engage with us via messaging throughout the webinar, please say hello in the chat. Let us know where you're joining us from. And I also want to announce at this time that a recording of the webinar, as well as a Q&A document, will be available on our website next week. And we'll let you know by email when that happens, so do not worry. So if you're not familiar with RTDS Technologies, we are based in Winnipeg, Manitoba, which is a research hub for HVDC technology in Canada. And we pioneered real-time simulation for the power industry in the 1980s by creating our technology, which is called the RTDS Simulator, or Real-Time Digital Simulator. And the original purpose for the tool was HVDC control testing, but the applications have expanded considerably, and the technology is now much more widespread. Today there are close to 500 institutions using this technology in over 50 countries worldwide. And we have four main categories of user: electric utilities, power system equipment manufacturers, research and learning institutions, and consulting firms. And all of the major protection and control manufacturers are currently users of the RTDS simulator. So this is just a few of the bigger names that are shown here. And these companies have really integrated hardware-in-the-loop testing into the development and acceptance testing process for their protection equipment, including generator protection. Basler Electric, for example, has done HIL testing of their commercial AVRs, and Schweitzer Engineering Laboratories recently completed extensive validation testing of the SEL 400G relay, which has transverse differential protection and turn-to-turn fault detection. So it's their recently released advanced generator protection system, and that was done with the RTDS simulator. Here's a look at just a few of over 100 utilities worldwide who are RTDS simulator users. Generator protection and control testing is a major area of interest for utilities with the simulator, and I'll show a glimpse of a case study from BC Hydro in just a moment. We also have well over 200 research and educational customers worldwide, just a few of which are shown here. And there are several different academic papers that have been done on machine modeling and testing with the RTDS, and we have a full list of technical publications available on our website if you're interested. I won't go too deep into the background here, and if you're not familiar with EMT Simulation or RealTime Operation, I suggest you check out some of our introductory presentations online. But of course, there are different types of simulation in the power systems context, and these need to be chosen based on the phenomena of interest to the user. So load flow and transient stability analysis, for example, give you phasors around the fundamental frequency as an output. And these solutions can accurately represent steady state and slow transients on the power system, for example, machine swing. What differentiates electromagnetic transient, or EMT simulation, is that it provides a time domain output. So there's a time-varying, instantaneous value output of the simulation, and it ideally gives you a waveform like the one shown here, which matches the current or voltage waveform from the circuit if it were to be measured from the system with a scope. And this allows for a greater depth of analysis over a wide frequency range and the ability to reproduce fast transients on the power system, such as a state or ground fault in a generator, for example. And the higher the sampling frequency of the simulation, the higher frequency results you can accurately reproduce. So we call the period of the sampling frequency, the distance between two consecutive outputs, the simulation time step, or delta t. And the typical time step for the RTDS is in the 25 to 50 microsecond range. We can also represent the high frequency switching of power electronics, and to do that we need to use a time step closer to the 1 to 3 microsecond range. And we can do that in our sub-step environment, and machines can be simulated at that time step as well, which Ali will tell you a little bit more about. Now to define real-time operation. When we say real-time, we mean the computer needs to solve all of the equations for the network in real-world time equal to or less than the simulation time step. And this means the real time for a power system event to occur is equal to the simulated time. Offline EMT simulation programs run on standard PCs rather than using dedicated hardware, so the time they need to complete these simulations is greater than, or sometimes less than, the real event time, depending on the complexity of the case. And that's one of the advantages of real-time simulation: efficiency. When running longer simulations, including slower acting dynamics like machine startup, the simulation time might become very large using an offline tool. But beyond efficiency, the principal advantage of running simulations in real time is the ability to connect external hardware to the simulation and test it in a closed loop. And closing the loop means not only observing the response of a protection or control device to an imposed signal, but also interfacing the device's response back into the simulated network. This type of testing, also called hardware in the loop or HIL testing, is only possible if we are updating the inputs and outputs of our simulation continuously in real time. It's not possible with a non-real-time modeling tool or with open-loop testing tools like a relay test set. Running a real-time EMT simulation is a very computationally intensive process, and it can't be achieved on a standard PC. So the RTDS simulator is built on dedicated parallel processing hardware, specifically integrated for the real-time simulation application. Our current hardware generation is called Nova Core, and it's based on IBM's Power 8 multi-core processor. So when the demonstration runs later, you'll see the software side of things on Dr. DeCordy's PC, but not the specialized hardware that the executable code is actually running on, and it looks like this. We achieve modularity through core licensing, so the quantity of cores licensed on a given unit determines the size and complexity of the simulation it can run. And in order to connect the simulation to external equipment, say a generator protection relay or an exciter, we use modular input and output cards, which are shown on the right. So for example, here you see an analog output card, which might be used to send power system voltages and currents to a real relay in the laboratory. So here's a diagram of what generator control testing with the RTDS can look like. Here we're simulating a simple network with the transformer down to the generator. We're taking voltage and current via instrument transformer models and bringing those signals out of the simulation via analog output, where they can then be amplified and input to a physical static exciter at secondary level. And the exciter's control signals can then be input into the simulated rectifier bridge via a digital input card. And the dynamic response of the machine and the network can be evaluated in real time. I wanted to briefly mention our protection and automation library as well, to make it clear that these experiments can be done with a mixture of hardware and software. So we have generic relay models available. You can see there we have a generator relay model, as well as an extensive library of generic exciter, governor, and power system stabilizer models, including IEEE standard models. So what's shown here is a small selection of our larger library in RSCAD. So the user can combine physical with simulated protection and control in the hardware-in-the-loop testbed. I also wanted to point out this sample case, which is available in RSCAD for any RTDS simulator users. It includes a 60-page guide which walks the user through the details of testing an SEL 300G generator protection relay. So here you can see the simulation circuit where a 22 kV synchronous generator is connected to a source through a transformer. Phase A of the machine has 3 sub-windings, and the connection points between them can be connected to ground through an impedance to simulate stator-to-ground faults, and the nodes can also be connected to each other to represent turn-to-turn faults. The stator and neutral currents, circuit breaker current, terminal and neutral voltages are sent to the SEL 300G via instrument transformer models that are connected to physical analog output cards. And the document also includes screenshots from the relay configuration software side that show how the relay itself is configured. The details of connecting to the analog output card are laid out in the document. You can see a photo there of measuring the voltage on a channel of the card prior to connecting it to the relay. And here we can see the response of the relay to a stator ground fault. The document shows the relay's front panel, the RSCAD software response, and the relay's measurements as well. So I just wanted to make users aware that this is available if you're looking for a more detailed HIL guide, because today's description is software only. Just before I wrap up, we recently came out with a little case study document showing off some work that's been done at BC Hydro, a utility on the west coast of Canada, with generator and transformer protection testing. So they had a diesel generator tripping on the differential element due to severe CT saturation on transformer energization. And they used the RTDS to validate the solution they put in place, namely a differential blocking scheme and the high security setting on the relay. So in the diagrams here, you can see they have tested stator ground fault protection here at 5% of the stator winding, and they've done batch testing of loss of excitation protection at various generator loadings as well. So you can find that document on our website. Now I'd like to hand it over to Ali, and he'll take you through the details of our machine models in RSCAD and our demo for the day.
Hello everyone, and thank you for coming to this presentation. My name is Ali Dekordi. The title of today's presentation is Electric Machine Models in the RTDS Real-Time Digital Simulator and their applications. We're hoping to have a series of presentations on the application of machine models. But today's work is on generator protection and excitation testing. The content of this presentation is Introduction to RTDS Simulator, Introduction to the library of electric machine models in RTDS, and demonstration of a case with generator protection and excitation control. As many of you know, real-time digital simulation is a fully digital simulation where all calculations required to determine the transient state of power system and servicing of IOs are completed within a time interval equal to the simulation time step. In this simulation, results are in synchronism with the real-world clock, and that is necessary for closed-loop testing of equipment. The underlying solution algorithm for RTDS is based on Dummel algorithm, which is used in other electromagnetic transient programs as well. In this method, differential equations of elements are discretized and represented by Norton equivalence, resulting in a network of resistances and current sources. Nodal analysis then is used for solving the network. Sometimes sophisticated elements are modeled as current sources only. Part of one of this presentation, now we move on to the introduction to electric machine models in RTDS. In our solution, we used a method called coupled electric circuit approach. Here, machine is treated as a set of mutually coupled time-varying inductors. If you look at the figure here, you see machine is decided by a set of windings on a stator and rotor, and the dynamics of the machine is decided by relation between voltage and currents. Voltage, vector of voltages, is resistive drop plus derivative of flux linkages. And the flux linkage is defined by inductance matrix. So as long as you know the inductance matrix, the dynamics of the machine can be determined. Now for an idealized park machine, the windings are perfectly sinusoidally distributed and the permeance is also sinusoidal. D and Q axis equivalent circuits may be extracted. When it comes to inclusion of machine model into the network solution of RTDS, we have two main approaches here. One is called interface-based approach, where voltages from network solution are received, machine is solved, and the stator currents are injected back to the network as a current source. The method is simple, however it has some time delay effects which can be mitigated with the use of snubbers and certain integration algorithms. A more precise approach is embedded phase domain approach. Here, if you remember from integration of simple inductor in Dummel algorithm, where trapezoidal integration applied to the differential equation of inductor. Now we treat the machine as a set of mutually time-varying inductors. And if you precisely apply the mathematics of integration here, you can represent the machine in discretized form as a set of current sources and a conductance matrix. This method is more computationally extensive, however, mathematically more precise. Also allows possibility of modeling internal faults. Here is a view of library of electric machine models in RTDS. Most of them may be used both in main and sub-step modules. If you are not familiar with main and sub-step modules, main step is used mostly for power system, around 50 microsecond. Sub-step, if you have high frequency switching of power electronics, you're advised to use sub-step. You can go to very low simulation time step. In this figure, on the left side, you see more commonly used machine models. Mach V31 synchronous machine. As you see how one can use it connected to a multi-mass. Induction machine for three-phase induction machine for loads. Two-phase or single-phase induction machine that's used for air conditioning. You have another three-phase induction machine. With this one, you can dynamically change the MVA and also have embedded breakers. Also, you have access to both ends of the windings if you want to change the delta or Y connection of the winding on fly. Here's a DC machine. On the far right, we have polyphase machines, both symmetrical polyphase and multi-star machines. Such machines have applications and new schemes of renewable energies, electric ships, and electric vehicles. The subject of today are machines for protection, machines with internal fault, which in the next couple of slides I will describe them. Here we have description of the PDSMFLT version 3, the model we developed in 2017 based on more enhancement to the previous versions. As a user, you could allow the machine to have no faulted points, 2 faulted points on each of the stator phases, or faulted points on all of the windings, or 2 faulted points on the field. You could move the location of fault between 1 to 99%. An application is for generator and motor protection, stator turn-to-turn, phase-to-phase, and phase-to-ground protection, and protection of the field winding. In 2018, based on customers' request, we enhanced the model further. Now you could include parallel windings. You have the possibility of modeling series faults, and the fault is basically causes opening of the junction, and modeling of machines with inherent asymmetry, where the original angle and the number of turns in the winding is deviated from the balanced design. An application is generator and motor protection, a stator turn-to-turn, phase-to-phase, and phase-to-ground protection, protection of the field winding, and protection of parallel winding and series faults. At this point, I'm going to stop the PowerPoint presentation, and we will move on to a demonstration of a generator protection and excitation case. We're going to have a demonstration for generator protection and excitation. If you are a user of the RTDS simulator, or if you're familiar with RSCAD software, you probably know that there is a samples directory within the tutorial examples. We have 2 folders related to this subject: generator brushless excitation system and generator protection and excitation. The first one is more comprehensive and is beyond the time of today for explanation, but if you have time in the future, you can take a look at it and experiment with it. For today, we're going to use generator protection and excitation folder, one PDSMV2 and PDSMV3, which is the newer version of the model. There's a case called PDSM underscore relay underscore stat underscore exe underscore 4. Let's open that. This is a typical case for a generator connected to AC system through a step-up transformer. Here, a grid is modeled as a source behind impedance. Here is your step-up transformer, your breaker. Here's my generator. The excitation system here is modeled in detail. If you're familiar with the simulator and MACV31 model and other exciter and governors in the library, let me expand it. There's a folder called generator controls, and you have access to typical standard excitation, exciter models, and governor models. In this particular example, we wanted to model the excitation system in more details. So in addition to the control part, we're modeling the excitation system as well, the valve group that rectifies the voltage to DC. If you're looking at this machine model, the field winding can be directly connected to excitation system. In MACV31, you would receive the excitation in the form of control signals in normal values. But here, if you click on the model, I can choose machine model field excitation type to be power system node or control system input. Control system input is similar to MACV31. Power system node, I have direct access to field windings. If you choose that, you go to this parameter called field current for 1 per unit unsaturated open circuit terminal voltage. And you put the required current for that terminal voltage. Using this, we can calculate the turn ratio between a stator and rotor and model the machine in details. The rest of parameters are similar to MACV31. For example, we could choose the format of electric data to be reactances and time constants or reactances and resistances. You could also choose the type of fault that you want. You want 2 fault on phase A, or phase B, or C, or field winding, or fault on all winding. Now let's look at this excitation system. AVR, or the control part of excitation system, is modeled here in this box. We're receiving terminal voltages, filter them, compare them against a set point, putting in a simple PI controller, and find out alpha order for 6-pulse valve group and prepare fire impulses for that valve group. Excitation is done, the rectification is done through the 6-pulse valve group, which receives the fire impulses from my AVR. Now that fire impulse could come from inside the simulation or from external components. These are my fire impulses. If you're using this case to test the physical AVR, you set this component to receive the fire impulses directly from your device. When you look at the circuit, you see if my goal is to start this machine from 0 speed, 0 excitation, bring the speed up, bring the excitation up, and synchronize this machine to the network, close the breaker on it. Right at the beginning, when my speed is 0 and my excitation is 0, I have no voltage at this terminal to be able to rectify and excite my field winding. For that reason, we have a circuit here called field flash circuit. And right at the beginning, we close this breaker on it, on the field winding, to produce some current into the field winding and eventually some voltage. And that voltage can be used to be rectified and applied to the field winding. On the governor side, you see my machine is connected to a multi-mass. In reality, you have a machine field winding, excitation system, and various stage of turbine are on the same shaft, which is modeled by this multi-mass. Torque comes from governor and machine, and the speed is decided by the multi-mass passed to the machine. Now the control part of the governor is here, and the way that is designed is that it's also simple. We're controlling the frequency or speed of the machine, and the order of power that applied to the machine to produce certain amount of power. However, if the breaker is open at the terminal, we don't want to apply torque on the shaft to accelerate it. That's why you have a small value here in case the breaker is open. Other components that you see in this circuit are fault components for external fault and internal fault between a stator to ground, or if you want turn to turn or face to face fault. CT to measure breaker current, CT to measure machine current and neutral current, and PT to measure machine terminal voltage. Also, you have fault logic, and using this fault logic, You can decide the type of fault, point of wave, duration of the fault, and location of the fault. In addition, you have a relay model here. You could use this case to test a physical relay, or in the case that we have here, we have a generic relay model of a generator protection, and we're going to test some of its functionality. For example, we look at relay elements. You could say stator differential, or 100% stator to ground, or loss of field excitation is enabled here. And we're going to experiment with a couple of them. Now I'm going to compile this case and go to runtime and demonstrate the simulation of this case on real-time digital simulator. Now any part of this circuit, for example, if you want to take the AVR out, you have a physical AVR and you want to test the functionalities using RTDS, or if you want to test the relay, you could take out and interface through IOs to test the functionality of your device, which we have done in the past with on customer side or in the lab. At this part of the presentation, we're going to show the runtime simulation of the case that we've shown in the draft, generator protection and excitation. Let's hit the play. If you remember, the goal of this simulation was to start the machine from 0 speed and 0 excitation and synchronize the machine to the network and close the breaker. Once the simulation starts, you'll see that speed starts from 0 and reaches its rated value. Now here's my speed coming up, and eventually I reach my steady state rated value. Now if you see down here, here is metering for excitation. I have no rotor field current and bus voltage is at 0. If you remember, to start this excitation, I have to start with flashing the circuit. I'm going to lock all my plots first. And I'm going to flash my circuit and start the excitation system. And you see I have rotor field current built up, and after that my voltage is building up at the terminal. My set point is 1.01, and that's what I reach, 1.01 per unit at the terminal voltage. Here is my voltage at the terminal of the generator and voltage at the AC system side. See the frequency of the generator, I keep it slightly higher than the system because right after closing the breaker I want to immediately push power into the system. What you see here is a synchrocheck vector display. A vector display is one of the monitoring features that you have in runtime, and you can use it either polar inputs or real imaginary input of a signal, of a vector. Now these input signals come from my relay monitoring. When you see here this synchrocheck element, make sure that the moment that I'm about to close the breaker, the synchronization signals are satisfied. So when I put the command for closing the breaker, it waits, and when it's ready, it closes the breaker. Now my breaker is closed, and you see my power is ramping up to the desired value of 85.85 per unit out of this 555 MVA, which is around 470 megawatt. And my reactive power is around 80 megawatt. Now, next thing we'd like to do is that I'm going to open the plots, and let's see, I want the finish time to be 0.2 every 2 points. And let's take a look at our signals. So I'm going to re-update all my plots. That, because I'm recording at the same time, it may take a bit longer than usual, but we'll wait. Now my plots are updated. Here is the excitation system. Is my bus voltage, rotor field current, field voltage, and these are the pulses, firing pulses that come to the valve group. If you're testing a physical AVR, usually a lot of times you send these pulses from AVR to the excitation system simulated on the machine. Here we have terminal voltages and machine current, the stator currents. See, this machine is faulted machine model. iMac A1 and A2 are stator currents for phase A, but portion A1 and A2 of the sub-windings. Right now, because there is no fault, they're identical. Now, next thing what I'm going to do is that I'm going to extend my time that I'm capturing signals to say 5 seconds. And I don't want all the points. Also, what I'm trying to do is to simulate loss of field excitation. To do that, I'm going to block all the firing pulses going to the excitation system. Once you lose excitation on a synchronous machine, on the rotor side, the stator tries to compensate for the loss of field on the rotor, and that draws more current on the stator. It's abnormal operation of the machine, and to detect that, there is one method called the Mo element, and basically you look at the terminal and look at the voltages and currents. Impedance seen from that terminal changes, and you can detect that through that impedance measurement. You see, if you look at the vector of current, they're going to increase. So I'm going to block the firing pulses. And you guys watch the vector display for the currents that you see here. And then breaker detected and opened. Now we wait for the plots to update. Now if you see, my plots are updated. Here is the characteristic for the Mo element for loss of field excitation. The black curve is the trajectory of impedance, and green and blue plots are the more characteristic that for zone 2 and zone 1 that we're considering. Let's redraw this curve if you're interested. See, trajectory starts from somewhere here. Then after we lose the excitation, it starts moving towards the zones that we define. Zone 2 is an alarm. Zone 1 is a trip, opens the breaker. If you look at the trip signal and information from trip signal coming from the relay model, you see a trip signal came, and element number 16 is activated. If you look at the manual for the relay model, that is number 40, loss of field excitation. Here is the excitation signals. Here's the time that we had our fire impulses. And right after that, we blocked them, we lost them. Our rotor field current started dropping. You see rotor voltage, we lost the rotor voltage, but it's sort of short-circuited. It lost the field, but it pushes the current through a stator to compensate for it. Now let's do another experiment. Let us go back and make our finish time 0.2 seconds. Number of points every 2. Let's lock our plots again. We need to flash the excitation again to bring the terminal voltage up. Reset our breaker and close it. Wait for the power to ramp up and reach steady state value. Next experiment, what we would like to do is simulate an internal fault on the machine between a stator to ground. And for that we have the element 100% stator to ground protection, but since we have high impedance, we're going to use the neutral over voltage. The location of fault at this point is 50%. So I'm reaching a steady state. My fault is on the internal fault. Location is 50, duration is 0.2. And I'm going to open my plots and apply a fault. Apply my fault. Relay is going to detect it and trip my breaker. And my plots are updated. Number 14 is detected. You should check the manual for the appropriate definition of the signal. If you're looking at the waveforms here, let's zoom. See, before the fault and after the fault, two parts of winding on phase A still have the same current because I have high impedance on my neutral. However, neutral voltage sees a big increase, and that's tripped the relay. And this is the time that's detected, this is the time that's tripped, and I lose all my currents. Here's two examples that we wanted to show you. There are more other things that we can do with this case and experiment with it. However, we're short of time. I'm going to stop this demonstration and answer your questions. If you need any further information, I can help you with that. Thank you very much.
All right. I hope everyone can hear me. Thank you very much, Ali, for the presentation and the demonstration. And thank you to our audience for joining us and for your attention this morning. We haven't gotten that many questions today so far, but we do have some time left before the end of the hour. So I encourage you to drop a question in the Q&A for Ali. We also have this poll question that's up on the screen that you should be seeing. We're kind of wondering whether you want to see more webinars that are more modeling focused versus HIL demonstration webinars. So please feel free to give us your feedback on that. In the meantime, Ali, do you have any comments for the audience at this point?
Hello, thank you everyone for participating in this presentation. Thank you for your time. What I would like to do is, I've been to a lot of customer sites and I've heard questions from customers. I have a bit of concern that maybe some people don't have a clear idea how to set parameters for machines. And if you want to use a synchronous machine or induction machine, you want to model certain dynamics. If you're interested in that kind of question answer period or webinar, I'll be happy to help you with that. Also, if you're interested in other applications such as multi-phase machines for electric ships or renewable energy applications, some of the newest schemes, we can also come with some presentations and maybe question answer period, or if different kind of webinar if you're interested. So maybe in the chat or whatever Katie is suggesting, please let us know how would you like us to proceed. Now I see a question from Anildo that I'm going to read and answer. Katie, would you like to read it or should I read it?
Sure, I'll read out the question from Hanildo Barros here. The question is about modeling very large power systems to take advantage of a network reduction. Dynamic equivalent synthesis for a huge number of different generators is not an easy task. As an alternative, a co-simulation environment for solving EMT and TSA subsystems seems more convenient. The RTDS platform has been providing this option under an FDNE-based EMT TSA interface. Can you give some details about the embedded TSA program adopted by the RTDS and the implementation? Ali, you can give some comments, and then if you want, I can add some thoughts as well.
Anil, is it the question, I think, is it our recent solution, our EMT TSA solution that we're considering, or is the FDNE part? I'm not sure what Anildo is
I think
referring
this
to.
question is referring to our more long-term solution for this. We have a fairly recent development in the last few years that involves a FPGA interface to a TSA simulation that runs on the user's PC. So we call this the TSAT RTDS Interface, or TRI, and it uses PowerTech Labs software, which is called TSAT, Transient Security Assessment Tool. And TSAT runs on the user's PC, and it runs the TSA model, and then an FPGA card in the PCIe slot of the computer creates a real-time interface with the EMT simulation running on the RTDS. So that's probably a more recent development that is available for doing this kind of work.
Well, thank you, Katie. I'm just going to add a bit more on the last part, which the question is could you give more detail about the solver capability, machine and control models? Basically, that part of the simulation, the TSA part, will be similar to what transient stability assessment tool or that kind of solutions they provide, similar to that, both in terms of controls and the way that machine is modeled. Now we have another question from, I hope, Anildo, I hope answered you correctly or completely. If you have further, maybe you can drop a question in the chat or email us. We'll be happy to help you. We have a question from Dr. Bruce Rigby. There are two questions. One is, how would you use the model to test elements that use stator third harmonic voltages? So the reason that this question is asked is that there's in natural state, winding, coil winding has space harmonic. In addition to fundamental distribution of the winding, there are harmonics. And those harmonics, when machine rotates, and you have back EMF on them, you have harmonic voltages produced along the windings. And some of the elements in protection, they use these harmonics to detect the location of the fault, especially state of the ground fault when it is closer to the neutral. There are two ways for it. One is that you could actually, if you know the design of the machine, the way that the windings are distributed, if you have to calculate inductances as a function of rotor position and work out the space harmonics. And then PDSMV2 machine model has a hidden option that you can enter those inductance forms and then naturally generates the harmonics for you. That's the harder way. Another way that is, in the case in the samples data is there too is artificially generating these harmonics. And based on our experience and analysis, we know that these harmonics are almost proportional to active power and the terminal voltage. And based on that assumption, we generate these harmonics for each subwinding, and then you could use them to test the elements that they work based on third harmonic.
Excellent.
May I answer other questions?
Absolutely. You can move on to the question about dynamically changing the rating.
So Ali says, or Ali Reza, is it possible to dynamically change the MVA rating of a synchronous generator? Yes. The short answer is yes. If you look at the library in the induction machine library, one of them you could actually dynamically change there's an option to dynamically change the MVA of the machine. For synchronous machines, we didn't have any inquiry, but if you're a customer and you ask us, we could implement that as well. And that works for embedded phase domain models because dynamically we work out the inductance metrics and resistance metrics every time. So if you want to change the MVA, you scale your inductances and resistances, and that changes MVA naturally. Now there is another question from Bruce that maybe Katie can answer later. Enildo says thank you. And then we have Amir Reza Muhtadi. The question is, can you also simulate third harmonic component along the stator winding to detect faults in the last 5% of generator winding? I think I have answered that when I answered Dr. Brigby's question. I guess that's it. If any other questions, I will be happy to answer.
Yes, we'll stay on the line for a couple minutes here in case we receive some additional questions. We have a comment in the chat saying that it would be great if we can have a webinar on parameter setting for machines. So we will definitely consider that feedback when we're deciding our next webinars. We'll definitely have at least a couple more webinars on machine modeling. It looks like we have another question from Bruce Rigby here, Ali.
Can you use the open winding induction machine model to change this from star to delta dynamically to do a star delta Steiner studies? Thank you, Dr. Rigby, for this question. Yes, the answer is yes, and that's the main reason that this option is added. If you look at the library, the embedded phase domain machine model, there's an option to access both ends of windings, and that option has been added to a lot of new machine models that you see both three-phase, for multi-phase and faulted machine model. And that option allows for the induction machine allows you to change the connection to star and delta using a system of breakers dynamically. So if you know that when you start an induction machine, you switch from delta to Y based on the speed of the machine, and that can be done using this model. That is a legitimate answer, and yes, thank you. That is possible.
Excellent, thank you. Well, I think we're out of questions and we're coming up to the end of the hour, so I guess we will look at wrapping up. I want to thank everyone for your questions and your participation. And we look forward to our future webinars. We actually have a webinar 1 month from today on March 24th, and it will be about the HIL testing of a fault interrupter with a distribution feeder model. So it's actually going to be the SNC Intellerupter connected to the IEEE 123 bus case through a special interfacing hardware by Omicron. So that's a really interesting webinar, and I think when you exit this one, you will get prompted to register for the next one if you're interested. So thank you very much, Ali, and to our audience, and I hope to see you all again soon.
Thank you, everyone, and hope you have a nice day.